I, Suman Bera, research scholar in the Department of Mathematics at Jadavpur University. Today, I will present my work entitled Stability Analysis of Fluid Flow in a Narrow Confinement Application in Microfluidic Devices. These are the outlines of my presentation. I will start by analyzing what is microfluidics. Microfluidics is the science of manipulating very small amount of fluid inside channels having dimension from 10 micrometer to 1 millimeter. Because of their small size, the system required very little sample volume, consume less energy, and provide precise control over fluid motion. This slide shows the evolution of microfluidic over past several decades. These developments have significantly expanded the application of microfluidics in science and engineering. Microfluidics offer several advantages. It's enable miniaturization, portability, automation, reduce reagent consumption, lower cost, and faster analysis. These benefits make it highly useful in biomedical engineering, mixing enhancement, industrial process, thermal management, and environmental monitoring. To improve the performance of fluid devices, it is essential to understand when the flow remains stable and when become unstable. Motivated from this type of microfluidic devices, we formulate four problems on straight channel and curved microchannel flows. Here in figure A, the geometry shows the straight microchannel with aspect ratio D by H, and the whole system is rotating about Z axis. And the second one is the curved rectangular channel where the flow is along theta direction and the whole system about Z axis, and a transverse magnetic field is applied along R star direction, which is perpendicular to the flow. In this type of problem, we analyze the effect of rotation number, D number, and curvature and Hartman number on the flow instability. As we know, the all fluid flow is governed by the Navier-Stokes equation, which contains equation of continuity given in equation 1, equation of momentum given in equation 2. When a magnetic field is applied, Maxwell's equation are also incorporated to account of incorporating electromagnetic force, which is given in equation 3. This is the whole methodology of linear stability analysis. We first compute the steady base flow and introduce a small disturbance. After linearizing the governing equation with respect to this small disturbance, the problem is converted into a eigenvalue problem. If the growth rate, that is the imaginary part of omega, is negative, disturbance decay and the flow remains stable. If it become positive, disturbance grow, indicating the onset instability. This approach allows us to identify the critical Reynolds number, rotation number, and other like D number, and the effect of curvature, rotation, Hartman number, and slip length on the linear instability of fluid flow. After converting the eigenvalue problem, we compute the growth rate and plot it as a function of aspect ratio in figure A, as a function of wave number in figure B, and as a function of slip length and in figure C, and as a function of Hartman number, rotation number, figure D. From this figure, we can show that without rotation, there exists no unstable mode either way of the aspect ratio, whichever it is 0.1 or 10. But with rotation, we have unstable mode at aspect ratio 1, which is our main findings, and the growth rate increasing with effect of rotation and curvature, which is also increased with anisotropic wall slip, but its decay, that is stabilize the flow with Hartman number and slip length. From the growth rate analysis, we compute critical Reynolds number and D number from the neutral stability curve, and the curvature, rotation, and anisotropy as the destabilizing effect, and lower the critical Reynolds number and rotation D number, whereas the slip length and Hartman number has a stabilizing effect, which lower increase the critical Reynolds and rotation number. Then we plot some secondary flow pattern, which is a cross-sectional flow pattern, actually counter-rotating vortices, which notion for the mixing or instability. And for a high and low aspect ratio due to rotation, we have the strength, vortex strength are high, denoted by the vector length and the color, whereas the magnetic field has the destabilizing effect, and the vortex layer and the strain decreases with Hartmann number, whereas the counter-rotating Dean vortices due to curvature, which is shifting along with increase the Dean number due to curvature, and the strength also increasing as shown by the color. These are some conclusion. Actually, the aspect ratio has a significant effect on the rotational instability. Curvature and rotation has a destabilizing effect, whereas slip length and Hartmann number has a stabilizing effect on the flow instability. These are the 4 problems we saw. First one is published in Journal of Fluid Mechanics, and the second one is Physics of Fluid, whereas third problem communicated in Journal of Fluid Mechanics, which is under review, and the fourth problem under progress, which is communicated soon. These are some bibliography, and I am thankful to the ANRF India for their support to the project grant, and I sincerely thank Professor Gopal Chandra Sweet and Dr. Mutahar Reza for constant guidance and encouragement and valuable suggestion. Also, I thankful to the laboratory support from Jadavpur University Mathematics Department. Thank you all.